Here we're looking at natural logs and solving different equations. We've already solved some exponential equations. Now we're going to look at some different ones. So first I want to define what a natural log is. So that's when you have a log base e of x. We say that it's ln of x. So we rewrite log base e and we rewrite it as ln. I use a like a cursive L here just so that I don't confuse it with a 1 or something like that. So I have ln of x, or the natural log of x. So for instance, log base e of 5, we usually write that as ln of 5. And ln is a key on your calculator, so you can see what that would look like there, and you can actually evaluate this on your calculator. So if we wanted to do that, go into my calculator, the ln button for me is on the far column, like fourth from the top. So I have ln, and then I'm going to put in 5 and enter. Depending on your calculator, you might have to put in the 5 first and then press ln. So just make sure you're comfortable with how your calculator needs the syntax, needs the order in which you are plugging things in. All right. And then another logarithmic function that we rewrite or rename is called the common log. So if we have a log base 10, we write that as just log x. This is less commonly used than the natural log, but we still use it. And this is called the common log of x. So for instance, log base 10 of 57, we usually just write that as log 57. There's nothing wrong with writing it like this as log base 10 of 57, and you're welcome to if you want. But if you see it, a log without a base, that means it's a base 10. Okay. So we use logs to solve different logarithmic and exponential equations, and we often do this by switching forms. And we'll see more complicated examples later, but for now, let's just start with these. So here, we've got log base 5 of x is equal to 12. And oftentimes, it's a good idea to start with just switching forms. If you have a log function, you don't know what to do with it. So it's often a good place to start, even if it doesn't end up being what you needed. So I've got log base 5 of x equals 12, excuse me. And I'm going to rewrite that in exponential form. So that would be x is equal to 5 to the 12th, or that really, really big number. X equals 2, 4, 4, 1, 4, 0, 6, 2, 5. All right, this time our equation that we're trying to solve is given as an exponential, and I'm still going to switch it to log form. So whatever form you were given, try switching it to the other one. So in this case, I started with exponential. I'm going to switch it to log. So that means that I'm going to have 3x plus 1 is equal to the natural log of 33. Remember that the natural log is the log base e. Now, it's kind of weird, but log base ln of 33 is a number. It's a weird number, and it's something we're not used to and might not be able to really visualize or like imagine, like, is that 182? Is it negative 12? What is it? But it is a number. So if you have ln or any log-based function of a number, that itself, that whole thing is a number. So this is a number, as weird as it may feel. So we can solve for x now. So I'm going to subtract 1 from both sides. So I have negative 1 plus ln of 33. You could have written ln of 33 minus 1. The reason I didn't is because I didn't want it to look like that minus 1 was inside of the natural log function. So I wanted to make sure I distinguish between that, because negative 1 plus ln of 33 is very different than ln of 32. All right, and then I can solve for x by dividing by 3 here. And that's my answer. And like I said, and this cannot be simplified any further. So I can't cancel any 3 and this 3 here. And it's not only because of the 1. If this negative 1 were not here, I still would not be able to simplify anything about this ln of 33 over 3. And that's because, again, 33 is inside of the natural log function where the 3 is not. So this is the answer. You could plug this in your calculator to see what decimal approximation we get. Let's see, we've got negative 1 plus ln of 33, and then divide that by 3. 0.832169. So that's our answer here. 0.832169. I think I said whatever I said before.